Let's continue talking about prime ideals. Here's the definition. A proper ideal in R here is a commutative ring with identity. A proper ideal P is called a prime ideal if it satisfies this property, that whenever a product of two elements is in P, one of those elements is in P. And if you want to process this definition, you want to look back at this notion of divisibility among ideals. So let's recap that. If you have two elements in R, you say that A divides B simply if B is a multiple of A. So B is A times another element of C, and another element of R. B is AC. Now you notice that A dividing B simply means that B is a multiple of A, which translates into saying that B is in the ideal generated by A, which translates into saying that the ideal generated by B is a subset of the ideal generated by A. So we have translated divisibility simply in terms of ideal containment. And you turn that into a definition for general ideals. So if you give me some general ideals I and J, then I say that an ideal I, the ideal I divides the ideal J if simply that ideal I contains J. Okay. And further, if you have an ideal and an element, you say that the ideal I divides the element B if it divides the ideal B, according to the previous sentence. That is, if I B is a subset of I, the ideal generated by B. And you check that these three sentences directly generalize when you change one of the elements by an ideal. So these three sentences are also equivalent. I divides B is same as saying that the ideal of B is a subset of I, which is same as saying that B is an element of I. Okay. Once you have all this translation, let's see how this definition of prime ideal translates. P is prime if whenever A times B is in P, then A is in P or B is in P. So AB in P is same as saying P divides AB. You see? Right up here, this equivalence. And then this is equivalent to saying, this is equivalent to saying P divides A. And this is, the next one is equivalent to saying that P divides B. So this sentence here translates into that sentence. For all A, B in R. And finally, maybe a little more definition, not much, an element P in R is called a prime element if the corresponding ideal, the ideal generated by it, is a prime ideal. And if you unpack that, what that means is, so check P in R is a prime element if whenever P divides AB implies P divides one of them for all AB in R. And here I'm again talking about divisibility of between elements. So first example, of course, the prime elements in Z are the prime numbers. Prime numbers are exactly the numbers that have this property. And the prime ideals in Z are these ideals where P is a prime number. Okay. That's one. Two. We'll see prime elements in Fx, one variable polynomial ring over a field, are the irreducible elements, the irreducible polynomials. And so the prime ideals are the ones that are generated by irreducible polynomials. Fx is an irreducible polynomial. To get more non-trivial examples, we have to work a little more. Maybe before giving a few more examples, here is the first lemma. Which is really just translating the definition of prime ideal, but it's rather useful. Let's have a proper ideal. So when I put a not equal to sign, it means P is not R. So it's an ideal and it's not the whole thing. Say that then P is prime if and only if R mod P is a domain. Remember the lemma that we proved earlier, a proper ideal is maximal, recall. If you have a proper ideal is maximal if and only if R mod M is a field. And here is a similar statement for primes. P is prime if and only if R mod P is a domain. Why? Here's a proof. Sketch. What is the key condition for P being prime? AB in P implies A in P or B in P. That's the condition for all AB in R. Saying that AB in P exactly amounts to saying that the corresponding elements in the quotient equal to 0 in the quotient ring, where A bar here means A plus P, which is the image of A in R mod P, where pi, remember, from R to R mod P is the quotient map. So this statement, so the point is that when you go from R to R mod P, things in P become 0. So saying that this product is in P is exactly saying that the images of A and B multiply out to 0 in the quotient ring. And then similarly this amounts to saying A is 0 in R mod P. So maybe I should write 0 bar. And this translates into saying that B bar is 0 bar. So the definition of prime ideal translates this key condition for being a prime ideal translates into saying that whenever a product of two elements is 0, then one of them is 0 in the quotient ring. But that's exactly the definition for R mod P to be a domain. Remember, a thing is a domain if whenever a product of two things is 0, one of them is 0. So that's basically the idea of the proof. But the immediate corollary of this is that maximal ideals are prime. See, if M is maximal, then R mod M is a field. But a field is a domain. So R mod M is a domain. So M is a prime ideal. So maximal ideals are prime. Okay. So we have seen some maximal ideals before. So I can now write like this one this was ideal in two variable polynomial ring. This is maximal, hence prime. Can give you another one. If you just take this ideal, then we saw that the quotient, this was an exercise last time, that the quotient is isomorphic to polynomials in the other variable, and this is a domain. So this is also a prime, but not maximal. So here is your first example of an ideal that is prime but not maximal. So maximal ideals are prime, but not conversely necessarily. But we'll have a lemma later on that if you're in a PID, then maximal ideals and prime, every prime is actually maximal. So later on we'll show in a PID, primes are maximal. So if you restrict to these examples on the left-hand side, Z and Fx, our two main PID examples, then in those, prime ideals and maximal ideals are the same thing. In the first case, the prime numbers, ideals generated by prime numbers, and the second example, the ideals generated by the irreducible polynomials. Okay. And then I'll have one more lemma, and we'll stop. That we defined irreducible element a while ago. In a domain, an element is called irreducible if whenever you write it as a product of two things, one of them is a unit. So you cannot properly factor x into two non-units. And there's a little lemma that is rather useful that says that prime elements are irreducible, and in a PID, irreducibles are prime. So that says, once we prove that, we'll know that in the one variable polynomial ring, all the irreducible polynomials are actually generating prime ideals.